In this video, I'm going to show you how to solve the ALEKS problem called Understanding Concentration Cells. And if you're watching this video, it's probably because you've been stuck on this problem for a while. It is actually pretty tricky, but don't worry, I am here to help you out. I've looked through a few versions of this problem, and it appears to have the same format for every single version. There is a galvanic cell. It is made out of some component. ALEKS is a little bit vague about what the components of the cell are. It does give you the concentrations of both the left side of the cell and the right side of the cell. Be careful. Every version of the problem that I looked at, one of the concentrations was in units of millimolarity and the other was in just standard molarity, so you're going to have to look out for that. So I'm going to start by just kind of sketching what this cell looks like, just based on the description that ALEKS gave me. The left side of my cell has a concentration of 0.075 molar, 75 millimolar. The right side of my cell has a concentration of 1.5 molar. And both the left side and the right side of my cell are made up of the exact same component. Now, the only reason that electrons are moving in this cell is because the left side and the right side have different concentrations. Mother Nature does not like to have two different solutions with two different concentrations in contact with each other. So the electrons are just simply going to move in such a way that the concentrations of both the left side and the right side are eventually going to become equal. So that means that for my problem, the left side of my cell is the one that has a lower concentration, and that means that the concentration of the ions on the left side of my cell needs to increase, and the concentration on the right side of my cell needs to decrease. And again, this is just simply because the electrons are going to move around in such a way that the two concentrations need to equalize themselves, or will eventually equalize themselves. So you need to pay attention to your own problem. The side of your cell that has the lower concentration, that's the one where we're going to see the concentration increasing, and whichever side has the higher concentration, that's the one where we're going to see the concentration of those ions going down. So now we have to think about how exactly will the concentration of the left side increase, and how exactly will the concentration of the right side increase. This is where we're thinking in terms of redox. So in our cells, we have this unknown metal ion, and this particular metal ion has a 3+ charge. How do I know it has a 3+ charge? I am applying what I like to kind of call the crisscross rule, where the quantity of one ion is the charge of the other. So the quantity of my sulfate ion is 3, and that means that my metal has a 3+ charge. And that's sort of how I would tackle that problem. But honestly, if you're working on this type of problem, you're probably pretty good at predicting the charges on ions, so I don't need to explain that too much. So both of these cells contain this M+ ion. That's what that concentration is referencing. And that M+ ion is going to react with a total of 3 electrons to just produce that pure metal. How do I know it's 3 electrons? Because I've got a 3+ charge. Now, whatever ALEKS problem you're looking at, there is going to be a variety of different types of charges on these metals. There might be M2+, it might be M+, and you're going to have to vary the number of electrons based on whatever the charge of that metal might be. Okay, so this reaction right here that I have written out, this is a reaction that decreases the amount of ions in solution. So this would be a reaction for my situation that's happening on the right side of the cell, where the concentration is decreasing. M3+ plus 3 electrons makes that pure metal. On the left side of my cell, this is where my ionic concentration needs to increase. This is where I have the opposite reaction occurring. So this is where I have the metal turning into the M3+ ion and 3 electrons. And so your first step is just kind of assigning this situation. Whichever side of your cell, left versus right, whichever side has the lower concentration initially, that's the one that is going to be having this oxidation reaction where you're losing electrons. And whichever side has the higher concentration, that's the one where you're going to be doing a reduction reaction. Okay, so now that I've got that figured out, the next thing that I need to do is figure out which direction the electrons are going to be flowing in this process. So here we can see on my left-hand reaction, this is the one where electrons are being given up, and those electrons then are going to be flowing from the left side of my cell to the right side of my cell so that they can react with those 3+ ions. And that information right here is what I need to be able to answer the first question, which electrode will be positive. Now, initially, you might be thinking to yourself that the electrode on this side will be positive because this is where all the electrons are going, or excuse me, I said that backwards. You might initially be thinking that the electrode on this side of the cell is negative because that's where the electrons are going, and electrons carry a negative charge. And that's a logical thought process, but that is actually incorrect. The electrode for me, the electrode on the right-hand side is the positive electrode. That's my positive electrode. And the reason that it is the positive electrode is because this is where the electrons are being attracted to. So the electrons are always going to be attracted, because they are negatively charged, they're always going to be attracted to the positive electrode. And so if I know that my electrons are moving from the left to the right, then that means my electrode on my right-hand side is the one that is positively charged. And this electrode over here is negatively charged because it's the one that is repelling the electrons away from it. So that's half the question, and that's actually, I think, the hardest part of the problem. Once you get that much figured out, then the second part of the problem is going to be easier. To solve the second part of the problem, we're going to use the Nernst equation for a non-standard cell. The Nernst equation is E equals E standard minus RT over NF times the natural log of Q. And this E is what we're trying to figure out. That's this answer right here. Now, E standard is the voltage that the cell would be if both of the cells had a concentration of 1 molar. And you might be thinking to yourself, I have no way of knowing what that is because I don't even know what this metal is. But if both of these solutions had a 1 molar concentration, there would be no redox reaction taking place at all. E standard for this problem, for every single version of this problem, E standard is going to be 0, or at least every version that I looked at. So that's 0. And R is the gas constant in the 8.3145 version. I'm going to leave units off just to kind of save some space. The temperature is the temperature in Kelvin. So I have 273 plus 35. That's going to be my temperature, 308 Kelvin. And the N represents the number of electrons that are being exchanged in this reaction, which we've got that figured out. It's 3 electrons being exchanged. And F is Faraday's constant, 96,500. I'm not sure if it's okay to round Faraday's constant like that, but you can always be safe by using ALEKS's calculator to get like the exact sig figs on Faraday's constant. And then you've got the natural log of Q. Q is products over reactants raised to their stoichiometric coefficients, but I'm just going to give you a shortcut. When you're solving this particular problem, Q is always going to be your small concentration, which for me is 0.075, over your large concentration, 0.15, and you don't need to worry about stoichiometric coefficients at all, because whatever that stoichiometric coefficient might be, it's going to be the same on both the top and the bottom of this problem. So whatever the coefficient is, it kind of doesn't matter because mathematically it's going to cancel itself out. So this is the setup of the problem to give you your voltage, and I've got that plugged into a calculator already, and I am getting a voltage of 0.0265. Let's see, ALEKS wants it to 2 sig figs, so that's going to be 0.02. Actually, it's 0.06499 or whatever, so it's going to be I'm going to write all this down so nobody gets upset with me. It's going to be 0.026 volts to 2 sig figs. Now, if you get this far in the problem and for some reason you end up with a negative sign here, that just means that you mismatched these or like flip-flopped those numbers in when you were calculating Q. This number should always be positive. It is always going to be a positive number. So if you end up with a negative number, just go back to your Nernst equation and reverse these values, and that should give you a positive number as long as everything else is correct. Don't forget there is actually a negative sign here. So don't forget that part and make sure everything else is all right. And this is a really, really, really hard problem, so just be patient with yourself while you're working on it, and you will get through it.